This lesson is entitled The Change of Variable Technique. What we'll be doing is a definite integration using U substitution, a combination of the two. The title itself will tell you a lot about what we're going to do. X and Y, among other letters, are variables. And what we're going to do a technique of integration where we're going to change the given variable to some new variable. So see if that doesn't make sense at the end of this lesson to you. Now, we've studied the definite interval, and you're going to need that to understand this lesson. And we have studied U substitution. You're going to need that to understand this lesson. If you have an exercise such as find the antiderivative of 3x plus 2 cubed dx from 1 to 5, it would seem reasonable to first determine the integral without any numbers. In other words, use U substitution and find the integral. And then after you get that answer, apply the fundamental theorem of calculus, that is, treat it as a definite integral and put in 5 for your variable and 1 for your variable and find the difference of the two to get the answer. And that certainly is a possible way to do this problem. That will work, we say. However, there's a technique named, as this title tells you, change of variable, which is 1, more mathematical, 2, more compact and efficient, and 3, it's applicable to other topics in mathematics. So that's why we're going to pursue another way of doing the problem versus what you saw us allude to there at the opening. We want to make our point with this problem. Find the antiderivative of 3x plus 2 cubed dx from 1 to 5. Okay, in other words, integrate this from 1 to 5. So here's what we're going to do. First, we're going to do it by the non-change of variable technique. That is what we described there at the outset. We're going to take this interval. We're going to let U be 3x plus 2. That's your quantity. We're going to find dx by saying du is 3 dx, so dx is 1/3 du. And then in the place of u, we're going to 3x plus 2, we're going to put u. That gives us u cubed. And in the place of dx, we're going to put 1/3 du. We're going to integrate. We get 1/4 u to the 4th plus c. Then we're going to put the quantity 3x plus 2 back in for u, and that's the antiderivative. And so the antiderivative of that is this, but we want to do it from 1 to 5. So we're going to say then from 1 to 5, this is the answer from 1 to 5. And then we're going to put in 5 for x and do the arithmetic and get us as a 17 to the 4th power. And then we'll put 1 in for x, and that's going to give us 5 to the 4th. And we'll do the arithmetic. And there is our answer. And that's certainly a way to get that problem. So now we're going to go and see what the change of variable technique is all about. So we're going to take the same problem we just worked, and we're going to use the change of variable technique. So what we're going to start out the same way. We're going to let u be 3x plus 2. Okay, we're going to do the same thing with du is 3 dx, and dx is 1/3 du. So that means this problem is integral 1/3 u cubed du, just like before. But here's where the change comes in. We're going to say, since u is 3x plus 2, when x is 1, u is 3 times 1 plus 2, or 5. That's your lower limit. And when x is 5, u is 3 times 5 is 15 plus 2, or 17. That's your upper limit. And we're going to integrate this thing, which is 1/12 u to the 4th over 4. From 5 to 17, and then we're going to put 17 in for u and 5 in for u and do the arithmetic. And of course, we get the same answer. So what's different? Well, here's what's different. We never went back and put it back in terms of x. Why? Because we did not have to, because we made two changes. We changed this from x being the unknown to u being the unknown, and then we changed our limits from being the limits of the x to the limits of the u. See, we made two changes. By making two changes, we got on the right track, okay? And we got the answer. Now, what you want to make sure you don't do is put it in terms of u, but keep the 1 and 5. You will get the wrong answer. Or get these new numbers, 5 to 17, but then put it back in 3x plus 2 for u. You're going to get the wrong answers. If you're going to go from x variable from 1 to 5 to the u variable to 5 to 17, you've got to be consistent. You either change all the way or you don't change at all. But this is a much more compact way of doing it. When you do it the other way, it's kind of like you do superficial or scratch work, I might call it, and then take that scratch work in and it's substituted in to finish the problem. So this is known as the change of variable technique. We've changed the variable from x to u. We can do that as long as we change the limits from the x limits to the u limits. Now you say, not sure I understand. Well, we're going to work 5 more problems, and hopefully by then you will understand it. And we hope you will adopt this technique. If not, I guess the best we can say is we will be using the change of variable technique solely in working the problems here and not any other way. So let's go to the next problem. So I said, so let's look at some examples using the definite integration using change of variable techniques. We'll only work a few since we've already studied the concept. In other words, we don't need to work. We're not trying to teach you u substitution. We've already worked more than 15 problems for you using u substitution. So we're not going to do that again. You should already have that down or be on your way. What we're going to do is take 6 problems and teach you how to use this change of variable technique. So let's look at example 1. Let's do exactly what we did with the last problem. First thing we're going to do is we have a quantity 6x plus 1, so we're going to let that equal u. We need dx, so du is 6 dx, dx is 1/6 du. So this problem right here, which we've recopied here, is now 1/6 u to the 4th du, but we're going to change these numbers from 0 to 1, and here's what we're going to do. When x is 1, u is 6 times 1 plus 1, which is 7, and when x is 0, u is 6 times 0, which is 0 plus 1, or 1. So see, we've got our new limits. You don't necessarily have to show this, okay? It's pretty much understood. If you go from here to here to here to here, you know what you're doing. It's simple arithmetic, but we're going to be doing this here. Now, we find the antiderivative. We add 1, makes it a 5, divide by the new exponent 5, and 5 times 1 is 6. 5 times 6 is 30, excuse me. And then we have 1/30, this to the 5th power minus this to the 5th power, and there is our answer. Example 2, here's one with trig. What is the quantity to a power? The sine. So let's let u be the sine. Du is the cosine of x dx. So this is going to be equal to, the sine is u, so it's u squared. Du is the cosine of x dx is du, so this is u squared du. Now, when x is pi over 2, u is the sine of pi over 2, which is 1. And when x is 0, u is the sine of 0, which is 0. So it's 0 to 1, which is, we integrate 1/3 u cubed From 0 to 1, we put in 1, we put in 0, and our answer is 1/3. Once you get the hang of this, this is not bad. Example 3. Our quantity is the square root of x plus 1, so we're going to let u be the square root of x plus 1. So we let u be this, what's left over, dx over the square root of x. Well, let's take the derivative of this. Now this, remember, is x to the 1/2 power. When we take the derivative, we get 1/2 x to the negative 1/2, or 1 over 2 square roots of x dx. We want dx over the square root of x, so that's going to be a 2 du. So this thing becomes integral of 2u cubed du, but now let's find our new limits. Well, we just simply, when x is 9, we have the square root of 9, which is 3 plus 1 is 4. And when x is 4, we have the square root of 4, which is 2 plus 1 is 3. So there are our limits, which we put there. And now it's 1/2, 4 to the 4th minus 3 to the 4th. And the arithmetic gives us 175 over 2. Let's look at number 4. The integral from 1 to 2, 2e to the 2x dx. We're going to pull that 2 out simply because we are accustomed to doing that. So we have this. We're going to let u be 2x. du is 2 dx, so dx is 1/2 du. So this becomes 2, 1/2 e to the u du. But let's change our variables. So when x is 1, you get 2 times 1, or 2. And when x is 0, you get 2 times 0 is 0. And so now we put in 2, we get e squared. We put in 0, we get e to the 0. Leave this as e squared. E to the 0 is 1. Leave your answer like that. We really don't want a decimal equivalent. If they ask for a decimal equivalent, you can give them a decimal equivalent, okay? But otherwise, when a problem is as easy as this one, this is one of the easier problems, believe it or not, give the exact answer. Let's look at number 5. You know, something like this looks a little scary at first, but we've seen scary ones before when we were doing u substitution. Just relax, take a deep breath, let u be the quantity. Remember, the substitution is the only way we have right now of doing antiderivatives if it's not the exact one of the exact formulas we memorized or learned. So it's going to work out. So we let u be 9 plus x squared. du is 2x dx. We need x dx, so that's 1/2 du. So we're going to have 1/2 1 over the square root of u du. When x is 0, you're going to get when x is 0, you're going to get 9 for your limit here. And when x is 4, you're going to get 9 plus 16, or 25 for your limit there. So now we integrate. This is u to, we show an extra step. This is u 1/2 u to the negative 1/2. Now when you integrate this, you're going to add 1 to negative 1/2, positive 1/2, and multiply, divide by 1/2, which is multiply by 2, and that 2 you multiply by cancels with this 2, so you're just left with u to the 1/2. And we've got nice numbers here. They were chosen because they're perfect squares, and you got the square root of 25 minus the square root of 9, which is 5, minus 3, which is 2, which is a nice answer. It's not by accident we choose, when we have square roots and things, to give you nice answers. The reason we do that, it's not that you couldn't have something like a 5 or whatever, but we really want to not mess up the problem with tendency to want to go to using a calculator. We're trying, the thrust of this set of problems is to teach you the concept, realizing that if it didn't come out to be a nice answer, you have to live with it, okay? Example 6, this we're going to let u be the cosine. That's the quantity raised to a power there, so use the cosine. du is the sine, minus the sine of x dx. We want the sine of x dx, so that's minus du. So we're going to put u in for the cosine, so that's u squared. And this is going to be a minus du, so we have a minus du. And when x is pi over 4, the cosine of pi over 4 is going to give us 1 over the square root of 2. Okay. And when x is 0, cosine of 0 is 1. So we've got our limits there. Okay. By the way, we're using 1 over the square root of 2 rather than rationalizing the denominator, the square root of 2 over 2, for a reason you'll see. This is 1 over, let's leave it as 1 over the square root of 2 for our upper limit, and 1 for our lower limit. Now we're going to simply integrate. Now this is, we're showing this extra step. This is u to the -2. So when we add 1 to -2, we get -1, which is 1 over u divided by -1, and that negative sign in the denominator, -1 in the denominator cancels with this negative sign, so it's 1 over u. And then we're going to put in for 1 over the square root of 2 in for u, so that's going to be 1 over the square root of 2, which is square root of 2. And then 1 over 1, which is 1. And that's why we've written this as 1 over the square root of 2 rather than square root of 2 over 2. It gives us a nice answer without doing a little more arithmetic. Now, we've flown through this purposefully with the idea that you can stop it, you can look at it, you can make notes. You really don't need any more problems than this, because we're here trying to teach you a concept. We've earlier, as we said, shown you all the different types of things that you might run into using u substitution, but that's not the thrust of this lesson. This lesson is to acquaint you with this change of variable and realize it goes bang, bang, bang. You let u equal du, find your dx, and the only thing you have to do is go up to this, whatever u is, and put in your lower limit and get your answer. And if you have problems here, I guess we can use a calculator rather than not get the problem, anything done on it. And you let cosine x be pi over 4, and that happens to be 1 over the square root of 2, which you probably should know from your studying of the unit circle and trigonometry, but whatever. We are going to wrap up this lesson, and hopefully you will practice some problems and you will become adept at using the change of variable technique.